You'll notice students today, these are high school students who are doing job observations. So they're seeing what a physics teacher does on the days when he doesn't lecture, for the most part. But this is the one lecture they are going to see. We're going to review briefly the types of things that could be on the exam and then move on. On the last exam, believe it or not, all three of you did the same thing on the problem. It said to find if it was a maximum or a minimum, and all of you went to the method of finding where the maxima and minima are. The goal there was to find if it's a maximum or a minimum by using L'Hopital's rule, because it's 0 over 0 at the angle of 0. And so you have to use L'Hopital's rule to see if that 0 over 0 is going to be an actual 0, a minimum, or if it's going to be a non-zero value, which would make it a maximum. And in the case there, it turns out to be 1. So it was a maximum. Now, here's the things that we have that could be on the exam. Lorentz transformation information, relativistic addition of velocity, and the quantum mechanics that we've done. After I finish reviewing, I'm going to continue with quantum mechanics, stuff that won't be on the exam, right? I'm not going to give you stuff now and saying, I'll be ready for it in an hour. That wouldn't be fair. There's no point in asking you stuff you don't have a chance of knowing. So reviewing the first of the three things that could be on the exam, we had the space-time invariant for position. And that was found by taking the radius of an expanding sphere of light. And the radius could be calculated either as radius is equal to the speed of light multiplied by time, that's a terrible R, or using the Pythagorean theorem, square root of x squared plus y squared plus z squared. And once again, that's Pythagorean theorem in three-dimensional space. And so what we did is we made our invariant just subtracting the squaring both sides and then subtracting the x squared, y squared, and z squared. So we have 0 is the invariant. And so with that invariant, we were then able to come up with a transformation between x, y, z in time in one reference frame and x, y, z in time in another. If we had a lot more time, or if I just taught a lot faster, I would have given you some problems using 4 vectors and having you transform them. Just before class, I was talking with Aryan, and he mentioned the problem of a farmer who wants to get a stick that is longer than his barn into his barn. And so using our relativity, how can you get a stick longer than the barn into the barn? Do it real fast, because if it's going real fast, you have length contraction. And so the farmer thinks to himself, if I run, and I usually do this with 4 vectors, if I run at 0.8 times the speed of light, then my stick, if I run at 0.8 times the speed of light, my gamma is going to be, what was it? 1.6. And so I can quickly calculate, it's going to be the original length divided by 1.6, so it'll be shorter. But he makes a mistake, because when he starts running, what does he see happening to the length of the stick he's carrying? Okay, so he can run really fast. He sees the length of the stick staying the same, but what happens to the barn? Shorter, length contraction. He sees everything has gone awry. He sees the barn has gotten shorter and his stick is staying the same length, so it will never fit in there. But what do people standing on Earth see? They see the stick shrink so that it fits completely in the barn. So people standing on Earth look and they say, it fit in the barn. The farmer was right. The farmer runs through the barn, comes out the other side, and he's so frustrated because it worked just the opposite of what he planned and it never fit in the barn. How do you correlate those two? How do you make both of those true statements? It never fit in the barn and it fit in the barn, both being true statements.
one's true in one reference frame and true in the other reference frame.
They're both true in their own reference frame. So how can they both be true? Because it's pretty much a simple thing. Does the stick fit or doesn't it fit? And we have two answers. Not time dilation specifically, but that's the idea. The idea is if we use these four vectors and we take, okay, so one event is when the front of the stick reaches the back of the barn. And one event will be when the back of the stick reaches the front of the barn. If the back of the stick reaches the front of the barn before the front of the stick reaches the back of the barn, it's all inside the barn. And so when you do those measurements, you find that they both agree on pretty much, guys, both observers agree on pretty much everything except for what is simultaneous. The person on Earth says, yes, I measured at simultaneous times that it was completely inside. The person that was running with it said, no, you such an idiot. You measured the back of my stick way after you measured the front of the stick. And so, of course, you got it fitting inside because you didn't measure at the same time. You have to do it at the same time. So the two are correct because they don't agree on simultaneity, and the four vectors allows you to do all the calculations to see that, to answer and unwind why they both see it correct. Now, we didn't do those calculations. We only set up the equations that would allow you to do it. So since we never did a calculation with those equations, all that you're being held accountable for is getting to those equations. And the one thing we did use with them, which is the second part. So these are the equations that we came to. Remember, the stuff between here and here, there were many slides between here and here where we said, well, we should have a linear transformation between position and time. And we took the equations for time dilation, length contraction, and compared the length in this reference frame and the length in that reference frame to get to these equations. But we got to these equations for our x0 is speed of light multiplied by time, x1 is just x, x2 is y, x3 is z. And then the transformations between x and one reference frame and another are these. So these here are the Lorentz transformations, which we worked out in class. So you should be able to know what those are, understand them, and understand how you got there. I'm not going to make you do the full derivation, right? Because honestly, it would be probably pretty time consuming. You wouldn't get it right. Just because you can make one little mistake and then a half hour later, you're not to the answer. It's, again, not very beneficial if that happens. Then we use those to calculate the velocity addition equations. Now our nomenclature here is different than the nomenclature we used in class, but the equations are the same. So here we had the definition that u sub x is the speed of an object in the x direction. U sub y is the speed of an object in the y direction. U sub z is the speed of an object in the z direction. V is the speed of one reference frame with respect to the other reference frame. And so if I want to find the speed of an object in the primed reference frame, I'm going to have dx prime and dt prime. Or if I want to find the speed of the object in the unprimed frame, I have dx dt. Now, how do I find the relationship between those? Do you guys remember? Yay or nay? Okay, I'm going with nays then. I mean, there I saw a head shake no. So ux prime is dx prime dt prime. Well, here I only put the primes, so let's work with that. X prime is gamma x minus vt. So that means that I can write ux prime is equal to d of gamma, whoops, not t. So there I've substituted for x prime and t prime. Now we just take these and we say, let's add, I don't know what I did to change my pins, but they're all different now. Let's add over dt to each one. So this would equal, yeah, okay, I'm going to change it to orange because I like the orange. So gamma is only dependent on the velocity difference between the reference frames, and we're having a constant velocity between the reference frames, so gamma is a constant. Bring that out. dx dt. Okay, I need to thin this pin up as well. I do not know why everything's different. Probably Microsoft updated the software and decided, you know, you didn't want those pins you had set up. So there I've done the derivatives. And now it's just simplifying. Notice I have a gamma on top and bottom. Cancel those babies. Make this not as fat. What's dx dt? That's the ux. So I have, come back, ux minus v. What's dt dt? 1. So we'll just leave that over dt dt, 1 minus dx dt ux v over c squared. And we're done. So that's how we derive the velocity addition if it was parallel velocities. That is, if the velocity of the object is parallel to the velocity of the reference frame. What if it's perpendicular? How is it different? Go ahead, get a ladder. It does change. Our textbook says it doesn't. Textbook's wrong. It's taking a simplification that's wrong. What's going to happen is you're still going to have, you know, you'll put dy prime dt prime. Well, y prime is equal to y. So when you do dy prime dt, you just get dy dt. So the top is just going to be u sub y. But the bottom is going to be the same thing, the gamma 1 minus ux v over c squared. And so there's your answer. Right? So you do the same thing, except for instead of putting x prime on top, you put the y prime, which is simpler. So it's simpler to find the uy prime or the uz prime. Uy prime and uz prime, of course, are going to be identical in their nature because they're both perpendicular. Yes?
So, talking about the test, then, that's the type of derivation we're going to be doing, or we're deriving those equations that are given from
this would be potentially the type of derivation you'd be doing. I told you I'm not going to have you actually derive these because it'd be too fraught with error. You'd be unlikely to successfully complete it.
So the work you just did is something that's likely to get
that is something that, yeah.
Okay. That's a lot less scary than what I thought it was going to be.
Now, and so these are the resulting equations you get. And the final thing is the particle in the box. Now, with the particle in the box, what is this scary equation? The Schrodinger equation. This here is the Hamiltonian Very nice writing. Acting on wave function psi. The Hamiltonian is an operator that gives you kinetic energy plus potential energy. So this here is pretty clear. There's the potential energy. This here, when you do that second partial derivative on psi, it's going to give you the kinetic energy times psi again. Or as Nathan called it last night, some trident-like thing. So we apply the Schrodinger equation to our specific energy configuration. So for the particle in the box, we had 3 regions. 2 of the regions had an infinite potential energy. What did we find for the wave function in the region of infinite potential energy? 0. Now the wave function is telling us about probability. The wave function mod squared dx is equal to the probability of being between x and x plus dx. Now, if I have a particle in the box, what's the probability of the particle being in the box?
Pretty good.
Pretty good. We would call that 1 in statistics terminology. It's the probability of 1 if the particle's in the box, if it's in the box. So, since the probability of being in the box is the integral of psi mod squared dx, well, that's the probability of being between x and x plus dx, then the probability of being in the box has to be 1, and I have to just add that up over all of the space of the box. Well, how do we add up a continuous function? What do we call that? An integral. So this is going to be the integral over my box, so I'll put 0 to L. In truth, it's minus infinity to plus infinity, but psi with 0 outside the box, so that's why I only am going 0 to L of my psi mod squared dx. So that's called the normalization condition. Our wave function has to be normalized, which means the probability of finding our particle in all space has to be 1. It's a pretty simple rule. We had a couple other boundary conditions, only one that we actually applied here because we had an infinite potential. You know how often an infinite potential occurs in real life? Yeah, pretty much approximately never. But in the case of an infinite potential, you have a special rule. Here's the non-special boundary condition. Psi must be continuous. That means that you have your function psi, and it cannot go, okay, I have to change color. It cannot go like this. That's discontinuous at the edges of the boundary. You can have like this, but you can't have a discontinuity. A second boundary condition that always applies except for this case, so you got to love always except for in this case, is that d psi dx must be continuous unless v approaches infinity. So that's why we didn't use it in this case. So in this case, what did the solutions look like? The solutions look like this. And look, we clearly have a discontinuity in the derivative at that boundary. Right? So it violates that second boundary condition rule because it's an infinite potential. Now let's do some interpretation. looking at these wave functions, these are all showing the wave functions. What does that tell you looking at the wave function? Okay, the probability where you're more or less likely to find a particle. On the top one, where am I absolutely never going to find the particle? Not in the troughs. The places where the wave function is 0. So I'm not going to find it here. I'm not going to find it there, there, or here. Now, I made them thicker. They're obviously just points in the middle ones. And this one here I kind of missed there. So these ones in the middle are points, but I made them big enough so that they stand out here in my marking. So those are the places where it's not going to exist. The particle could be, if you square this, psi mod squared is going to look like, which is why it wasn't at the troughs, because the negatives, the troughs, are peaks when you square it. And so we have 3 locations where it can't be found, and then we have 4 locations where it's most likely to be found, equally most likely. The expectation value is the position that I would find for my average of measurements. So if I take 1,000 measurements of the position, and the probabilities are as illustrated here, where's the average of those measurements going to be? It's going to be at the center where the probability of it actually occurring is 0. So the average position, the most likely position, 2 different things. So we need to make sure we understand that. Here are the actual solutions. This is a normalized wave function if we choose A correctly. And in class, we did the normalization calculation. We did the integral from 0 to L of A star sine of n pi over ax times A sine of n pi over ax dx. And we set that equal to 1. And what that gave us was 1 is equal to A mod squared over 2. And so that means that A is equal to, and I put plus or minus, well, I didn't put plus or minus, just put square root of 2 no, I'm sorry. I mixed my A and L. A mod squared. That's what it is. Okay. That's how it came out. We did it before in class, so I was just trying to remember it here. And of course, I remembered wrong. And so we found this. Now, that's only one possible solution because my capital A could be a complex value. There was nothing that said it had to be real. I just chose the positive real root. So there's lots of other values that would make it work out, but they're just multiplying by a complex value with a magnitude of 1. How did we get this? How do we get this quantization of energies? Do you remember that?
Because they had equal 0. And they're doing the sine function.
It came from matching this boundary condition And it indeed had to do with the argument of sine had to be 0. And so we set the argument of sine is equal to 0 that gave us only certain values for the angle, which is where the quantum numbers came in. Because for sine's angle to be, or the sine to be 0, the argument has to be an integer multiple of pi. And so we had the stuff that sine was, that was in the angle, n pi over a, the length of the box here. Oh wait, this is going to the answer. Have to go back a step. We had sine of kx there. So we had kx has to be equal to an integer n times pi to match the boundary condition here. And so that gave us the condition that n pi is equal to kl. Therefore, k has to be equal to n pi over l. But k was a function of energy, which we don't have shown here because I didn't do the whole problem today. I'm just reviewing it. And so that gave us then an equation for energy because k was dependent on energy. K was square root of 2me over h bar squared. And there we have the quantized energy states. Okay, that's what we did last class period. I think we might have mentioned, yeah, we did because I did a quick hand wave at this here. Our solutions, we have sine of n pi over width of the box x, or sine of 2n pi, or sine of pi over width of the box x, or sine of 2 pi over width of the box x, or sine of 3 pi over width of the box x. Those are what we're going to have for our arguments in each of the different wave functions, each of the solutions. Another rule for quantum physics is that our solutions have to be orthogonal to each other. That is, if we were to do a dot product between the solutions, if they're two different solutions, it's like a dot product between x and y. Dot product is measuring how much is parallel, how much of x is parallel to y. 0. Same thing here. If I have n equals 1 and n equals 2, so I used m and n here to indicate the options. If m is not equal to n, then when I do the dot product, it's going to have to be 0. If m is equal to n, then it's going to have to be 1 for normalization. So we can do one integral that gives us both the orthogonality and the normalization condition. And that integral is this one right here. So we have the integral of psi sub m star, psi sub n over all x's. Now this thing here is called the Kronecker Delta. And it's equal to 1 if m equals n, 0 if m is not equal to n. So that's why one equation can represent both orthogonality and normalization. So together we call it the orthonormal condition. This here is using a trig identity to make the integral easier. You're going to have 1/2 cosine of the difference in m and n times pi over ax minus cosine of the sum of m and n pi over ax. Well, the integral of a sinusoid so sine or cosine over an integer number of wavelengths is always 0. Since m is an integer and n is an integer, m plus n pi over a is always going to be over an integer number of wavelengths is always going to give us 0 for the answer. The first one, m minus n pi over ax, if m is equal to n, then that's going to be, I'm just thinking here, then that's going to be just cosine of 0, which is 1. Well, integral of 1, well, that's not 0. So the only time when we don't get 0 for any of these integrals is when m is equal to n. And then when m is equal to n, we're integrating 1, going from 0 to L. So we get L for that integral, times the 1/2, of course, it's out front. And when you put it all together, you find that it gives you the normalized outcome because of your normalization constant. Now, new material. This is stuff that won't be on the test now because we didn't talk about it before. Yes?
So what kind of, before we move on.
Yeah, what kind of problems do you have?
Right.
So things that would be conceivable is I could ask you what the Schrodinger equation is. Now, that would be pretty simplistic. You'd probably have to have more than just that. I could ask you how to apply it. I could ask you to apply it to each of the 3 regions. Or I could say if you apply the Schrodinger equation to these 3 regions, you get these 3 solutions. Apply the boundary conditions to find the quantized energy states. I could say, you have the solution is like we just did, a sine n pi over, I'm going to use L and L in my speech, a times sine n pi over Lx. What does a have to be to normalize it? So things along those lines. Or I could ask you about orthogonality. Show that, psi 1 is orthogonal to psi 2.
So it's going to be less like derivations and stuff. It'll be more like questions about it.
Well, the one part was derivation. The one part where I said find the wave functions in each region. That is derivation. The others are not. You're right. Okay, so the new material. What is the value of this quantum mechanics? What have we found so far that would appear useful in quantum mechanics? Okay, it gave us calculations of the quantized energies. That's something that's useful to us. That's something that we can measure. In general, the quantum mechanics is only valuable to us or useful to us when it gives us something that's measurable, something that we can make measurements to say yay or nay on. And so we focus in quantum mechanics on measurables. And so we talk about observables. That's the term we use in quantum physics. And observables are things like angular momentum, position, momentum, energy. And so we have operators, functions that act on a function that will return those values. And so, for instance, that Hamiltonian operator returns the kinetic energy plus the potential energy. The energy operator, which we talked about the first day when we had the Schrodinger equation, the IH bar partial derivative with respect to time, returns the total energy. The position operator is the simplest one. If our psi, our wave function, is written in terms of x, the position operator is just x. So you'll notice here I have x psi sub n of x is equal to x operator psi sub n of x, because the x operator is just x. That's your easiest operator. Now, we talked about what the average value of a bunch of measurements of position would be. We can calculate it from our quantum physics. Before, we calculated simply what the probabilities for different positions were, and we looked at it and said, well, clearly I can see the average is in the middle. But we didn't do that mathematically. We did that visually. Mathematically, the way we do it is the psi mod squared is our weighting factor for position. And so I'm going to take this position times the probability of that position and sum that up over the entire range. Sum of the probabilities is 1, so I don't have to divide by anything. So that's how I find the expectation value, the average position, if I make a lot of measurements. And so mathematically, it's going to be, like I said, your position multiplied by the probability of being at that position integrated over all of the possible space. In practice, we write it in a different order. The probability, I said, was equal to psi mod squared. That means psi complex conjugate psi. Just to make sure it's really clear, because this is probably new to you, let psi equal A plus IB, where A and B are real. If that's the case, then psi star is equal to A minus IB. You simply change the sign of the term that has the imaginary number in it. And so what's the point of that? Well, if you do the math, you see real quick. Psi mod squared is equal to A minus IB times A plus IB, which is equal to A squared plus AIB minus IBA minus I squared B squared. Notice these here are 0. AIB minus IBA is just 0 because these are real numbers. Doesn't matter what the order is. And what is I squared equal to? -1. So this is just equal to A squared plus B squared. Psi mod squared is the magnitude squared of psi. And so that the psi mod squared doing the complex conjugate thing is to make sure that we're going to get the amplitude squared. But in our calculation for the expectation value, because the term we have is expectation value, not to be confused with expectoration value, which would be something having to do with spitting. So the expectation value is the integral of psi star, then the operator, then psi. The order is different because this operator acts on this to give me this value, right? Because x operator acting on psi gives me x value times psi, then that order will contract down to the value of the measurement I'm trying to make times psi mod squared. So for position, that's pretty easy to do. For momentum, the momentum operator is equal to h bar over I d dx. So if I want to find the expectation value for momentum, what do I need to write down? Well, just lead me through what's the first thing I should write down. Look at the line above. What's the first thing I wrote down? Okay, so I had integral sign. Then what? Psi. Star. Put the star there. Then what? Then comes the operator. And the operator is going to act on and then I finish up with dx. So using our solution for this problem, I'm just going to continue on down here. I can't use A and L as separate entities because they're the same. And to color coordinate things, what would you do now? Well, I used to do the derivative. Derivative sign, of course, is bring out the n pi over L cosine of n pi over Lx. But I just realized this is actually really, really simple. I realized this because my son back there is taking calculus right now, and they're doing this. Let u equal square root 2 over L sine of n pi over Lx. du is equal to no, I only put the derivative sign in once. Because that's how you do. I mean, the partial. Okay, I put in the partial because if my psi has time in it, then I need to have the partial. Because my psi doesn't have time in it, the partial needs to have the same.
No, but what I mean is, you put in, there's a partial and dx.
Yes. Or if you prefer, like I said, I can make this a non-partial because I only have one variable, so it doesn't make a difference.
Oh, yeah.
And so I could rewrite this integral as, now I've never done this before, integral of u h bar over I du. He's not paying attention. H bar over I u squared over 2, right? And then I put in my limits from 0, from not u, but from, yeah, let's substitute back for u. It's u initial to u final. So I have that. Well, what's sine squared of n pi over L times L? In other words, sine squared of n pi. Sine of n pi is always 0. That was how we actually found the quantized energies, because so 0 minus the sine of 0 is 0 equals 0. So our expectation value for momentum is 0. That, of course, makes, once again, logical sense, because we're going to have perfect symmetry between them going left and going right in the box. And so the average should be 0 if I measure all the momentum. But that's how we calculate the expectation value. Now, it's real simple for the cases I've done because I was doing real simple cases. In more complicated cases, like, let's say, the hydrogen atom, you don't get these simple, oh, it equals 0 results. I've talked about the orthogonality requirement of our solutions. Another requirement of the solution is completeness. And you're like, completeness. Well, you may or may not have seen a movie with that famous line. You complete. Yes, no? Well, it was original to, what is that Tom Cruise movie where he's an agent and Cuba Gooding Jr. is the athlete. No. I wish I could remember. I can't remember the name of the movie. You had me at home. Show me the money. All lines from the same movie.
I mean, they're pop culture.
Yeah.
So
But you don't know where they came from. Excellent. And I can't remember because I've got holes in my memory the size of Swiss cheese, apparently. So that didn't work out either. As I just said, holes in my memory. I can't remember idioms. Okay, so what is completeness? Completeness means that you have all of the different unit vectors required to describe any location in space. So we live in how many dimensions of space? 3. So I need 3 mutually perpendicular variables or directions to describe my 3-dimensional space. We call them x, y, and z. Well, in a quantum physics problem, such as this one, how many solutions do we have for the particle in the box? We had n, and what was our limitation on n? It had to be a positive integer. How many positive integers are there? An infinite. So we have an infinite space, an infinite number of directions. But one of the rules of quantum physics is it has to be complete. Our dimensions have to be all of the possible dimensions in the space. Now, we're not going to sit down and prove anything to that effect here. Just to say that one of our requirements is that our solutions span all space, which means that I can take any function and write it as a linear superposition of these. Just like if I have a vector that goes from me to Nathan, I can say, okay, it's this amount in that direction, plus this amount in that direction, plus this amount in that direction. Each one of those directions was orthogonal. And they completely span the space, so I can get to him following those directions. If we only had 2 dimensions, like up and down and forward and back, it wouldn't be complete. I couldn't make a vector that goes to Nathan using only forward, backward, and up and down. So that's what completeness means. You have all of the possible directions in the space. And so you can just make a linear combination of those directions to describe any function. And so Dirichlet's theorem, sometimes the French words drive me crazy. Sometimes I like them. Dirichlet is one I like. Dirichlet's theorem is basically just taking Fourier's theorem, another French name, and applying it to quantum physics. He says that we can indeed make any function written in terms of these wave functions as long as the wave functions are complete. And we can find what those coefficients C are by using the orthonormal relationship. So here's what Dirichlet says. We can find the coefficients here by doing that integral. Now let's show what that integral is just to make sure it's real clear. So I have C sub n is equal to the integral of psi n star function of x dx, but function of x is equal to the integral, and I'm going to use a different index here. I'm going to use m. So I'm going to plug this function into that definition to see what my C sub n's are. So I'm going to have C sub n is equal to integral of psi sub n star times sum over m equals 1 to infinity Now, in this case, my m is not my variable of integration. What's my variable of integration? X. And so I can bring the summation as well as the C sum m out. But we have already seen this. What did that equal? That was that Kronecker Delta. It's either 1 or 0. It's 0 unless m is equal to n, which means that this summation is going to collapse down to just one thing, C sub n. Now you look at this and you're like, okay, I see that you went in a circle. Going in a circle, is that really beneficial? Yes, it is. Because in reality, your function f sub x is going to be something that's not written in terms of psi sub m. But if f sub x can be written in terms of psi sub m, then I can do this integral with the actual f, whatever that function is, and it will give me those C sub n's. We're out of time. I guess we'll have class next week because I want to go over, well, no, we won't. I only had 2 more slides, and I don't have any new material for next week, so we won't have class next week.